This video is going to look at rates of change, and in particular, two types of rates of change, the average and the instantaneous. Now recall that the average rate of change is simply the gradient formula. Okay, so this is essentially y2 take y1 over x2 take x1. And the instantaneous is similar, except what we do is we choose a second point and we make that second point infinitely close to that first point, which gives us the rate of change. So let's scroll through these notes and actually apply it. So we've got a function f of x equals 2x squared take x, and what we want to do is find the average rate of change between these two values. So the first thing I'm going to do is say m average, so the average rate of change is equal to f of 4 take away f of 2, that's y2 take y1, over x2, which is 4 take 2. Okay, so f of 4 is going to be 4 squared is 16, 32, 32 take 4, take away f of 2 is going to be 8 take 2, over 2. That's going to be 28 take 6, all over 2, 22 over 2, which is equal to 11. So the average rate of change between these 2 points here is going to be 11. Let's just review how to quickly do that on the calculator. So I'll just straight up define f of x equals 2x squared take away x, and we'll go shift divide to get our fraction key in, and we'll go f of 4 take away f of 2 all over 2, and we get 11. So that's how we're going to do it with the calculator, a really quick method of getting that average rate of change. All right, now what we want to do is do an average rate of change between 2 and 2 plus a value h units away from the original, okay? So what we're going to do is note that f of x is equal to 2x squared take x from the previous part. And I'm going to do f of 2, which I already know. The answer to that was 6. And I'm going to do f of 2 plus h, which is equal to 2 brackets 2 plus h all squared, take away 2 plus h. Right, now let's get the average rate of change. So m average is equal to, so it's this thing here, 2 plus h all squared, take away 2 plus h, take away 6. So that's f of 2 plus h, that's f of 2, all over 2 plus h take 2 is simply h. So this is looking a lot like first principles here without the limit, and that's exactly what it is. So we've got 2, 4h plus h squared, just doing the perfect square expansion, take away 2, take away h, take 6, all over h. 8 plus 8h plus 2h squared, take away h, take away 8. That cancels with that. I've forgotten to put it over h, which is 7h plus 2h squared over h. Let's factor out h. 7 plus 2h over h. Cancel them out, and our average rate is 7 plus 2h. Okay, now what we want to do is get the instantaneous. Okay, now there's a couple of ways of doing this. First way is to use that. So we're going to go limit as h tends towards 0. So we're going to make the distance here, this distance here, approach 0, i.e. get the instantaneous. So we're going to go limit as h tends towards 0 for 7 plus 2h equals 7. So that is going to be the instantaneous rate of change, but we can actually just use calculus. So f of x equals 2x squared take x, f dash x equals 4x take 1, f dash 2, so the instantaneous rate of change at 2 is going to be 8 take 1, is going to be 7, just like that. Okay, we've got a reservoir being emptied here. quantity of water V meters cubed remaining in the reservoir T days after it starts is this cubic. So what kind of a cubic is that? That's a inflected cubic. So it's sort of going to look like, what it's going to do, it's going to be 90 across, and that's going to move the inflection point. So I think what it's going to do is essentially come down like this, inflect at 90 and continue. This is going to be T and this is going to be V, and we'll chop these off here. So it's only the reservoir emptying that we're interested in. Okay, so that's kind of what we're expecting to happen here. So at what rate is the reservoir being emptied at time T? All right, well, what's that? That's just the derivative. At what rate? That gives you the rate of change at any time T. So let's just try to do some calculator work on this. I'm going to define my function, define f of x equals 10 cubed 90 take x to the power of 3. Now don't forget that we're changing variables here, so we need to be consistent on the calculator. We can't drop t's in, but we need to be consistent with the context of the question over here. So to derive it, we're going to go diff f of x. That's our derivative. Let's write that in. V dash t is equal to negative 300, or 3000 rather, x take 90 all squared. How long does it take to empty the reservoir? That's when V of t is equal to 0. So let's go and solve. As suspected, it's going to be empty at 90. T is equal to 90. What's the volume of water in the reservoir when T is equal to 0? So we're going to do V of 0, which in this case is going to be a pretty big number. So F of 0, yeah, massive. Let's use this as an opportunity to write this in scientific notation. So we're going to go 7.29 by 10 to the, now that's 1, 2. So 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8. After what time is the reservoir being emptied at this rate? Okay, here's a good question. Okay, so this is when the rate of change, or V dash t, we want to know when V dash t is equal to this rate here. Now, I'm just going to do something incorrect here first of all and show you what's going to happen. So I want to know when the rate of change is this. So let's go ahead and solve it. Solve. I usually just diff it first. I know I've diffed it earlier, but I diff it again, and I say solve with the derivative equals 3 times 10 to the power of 5. All right, and what I'm expecting to have happen here is it's going to say no solution. All right, and pause the video and see if you can see what's the mistake here, why it isn't finding out when it's being emptied at this rate. All right, if you've paused it and had a think about it, hopefully you recognize that it's never going to have a positive gradient. If we look at this function here, it's always negative. And the key thing is that the reservoir is being emptied. All right, and emptied means it's going to have a negative in front of this value here. This is the rate of change, but being emptied means as x or t increases, v decreases. So actually what we've got to do is slot a negative sign in here. Okay, and I'll do that on the calculator as well. And what it says is we've got two solutions at time t equals 80 and t equals 100. Now, the problem is that this is an out of domain solution because this happens down here somewhere, okay? And even though the graph says it's possible, we know that the reservoir is going to be empty at 90. We're going to say, but T is an element between 0 and 90 inclusive, so T equals 80 days. Yes, days. All right, we want the graph of V, T against T. We've done that already. All right, so here's my graph there. It's a bit of a dodgy one. So can you guys just in your notes down below on the Cartesian plane include the Y-intercept, which is when T is equal to 0. This is 7.29 by 10 to the 8. Okay, now what we want to do is grab the derivative. Okay, so what's going to happen here is we're going to have a negative rate of change along here up to this point here. So let's do the derivative graph. This is going to be t still, and instead of v of t, this is going to be v dash t. Right, now what we've got here is a 0 gradient point. Okay, so 0 gradient is going to be there. All right, because that's a stationary point of inflection at 90. And what function was the original? It was cubic, right? So that means that the derivative function is going to be a parabola. Now, what we've got here is a negative gradient here. So essentially it's going to come up. Came up a bit sharp there. So it's going to come up from here and get to this point here, like a parabola shape, okay? Now, because the original function was chopped here and had an endpoint there, its function is not differentiable at its endpoints. That should be an open circle. All right, and over here is the y-intercept of the derivative. That should be an open circle as well. And where is that circle? I'm just going to grab my derivative function and I'm going to say, can you chuck 0 in there for me? And that's where that happens at. So that endpoint there is when t is equal to 0, y or v dash t is equal to negative 2.43 by 10 to the 1, 2, 3, 4, 5, 6, 7. 10 to the 7. Just out of curiosity, I'm not sure what your calcs are put into, but I'm going to go basic format and make sure your calcs are in normal 2. I think if they're in normal 1, and I ask this question, no, it didn't do it for that one. What about this? No, bad example there. But can you guys just check that your basic format or number format is in normal 2? That's really important. In fact, did I set it then? Basic format, normal 1, set. Let's just re-ask that question. Yeah. No, so you want your calcs in normal 2. Basic format, normal 2. Set it. All right. So now onto some kinematics, and most students don't really love kinematics, and I've got to say it's not a huge part of the methods course. So we tend to avoid high-end kinematics questions and really want you to understand 2 basic things or 3 basic things. Okay, derivative of displacement function gives you velocity function. Derivative of velocity function gives you acceleration function. And that's all we really need to be comfortable with. Okay, so let's go ahead and do some work on this particular problem here. So we've got a particle moving along a straight line such that its position x relative to a point origin is given by this function here. So this function here, x of t, describes the position of the particle relative to time. And what we can quickly see, we can see it over here, this is the original function. We can see that the particle starts at the origin, okay? And this side of the Cartesian plane, or the positive values of t, we say that the particle is moving to the, let's go the convention, so the right of the origin, so the positive values are going to be to the right. So what happens is the particle moves to the right, gets to this point here, the turning point, changes direction, and it's still to the right of the origin, but it starts moving left, gets back to the origin here, and changes direction once more, and moves back to the, moves towards the right again, still on the right-hand side, but moving right. So the first thing we wanted to know is what times and in what positions will the particle have zero velocity? Okay, so what we're going to do is zero velocity means we get x dash t, 3t squared, take away 12t plus 9. And what we want to know is, so that's our velocity function. So x dash t is also our velocity function, and we're going to want to know when you have zero velocity. So 0 equals 3t squared, take 12t plus 9. 0 equals 3t squared, take 4t plus 3. 0 equals, I'm going to divide by 3 on both sides and get rid of it straight away. T take 3, t take 1. T is equal to 3, t is equal to 1. Now let's see if that sort of sounds right. There it is there, zero velocity there and zero velocity there, which means if you look at our second derivative, first derivative function, this parabola here, you can see it's got zero velocity there and zero velocity there. So it seems to be working. Now what we're going to do is do x of t to find out its position there, and the answer should be 4 and 0. Let's just see whether that's the case. So I'm going to slam it into this first one here. 27, take away, oh, I need to work that out. So I'm going to do not x of t, I'm going to do x of 3, which is 27, take away 6 lots of 954 plus 9. Is that right? 3 cubed. All right, yeah, rocket scientist over here, that's not 9, that should be 27. Okay, so 27, take 54, difference is 3, 23, 27 plus 27 is 0. Okay, that's good, that works well. All right, and then we're going to do x of 1. The answer should be 4 by the looks of it. Let's check it out. 1, take 6 plus 9 equals 4. Okay, so the coordinates are going to be 1, 4 and 3, 0, okay, which were reflected in the graph. All right, what we want to do is note the acceleration at those instances, okay? So if we look at those instances there, this is the acceleration function. I should be getting like -6 or something there, and I should be getting like 8 or 9 there. Okay, so I'm going to find x double dash t equals 6t take 12. I've just derived x dash t to get that one. And this is our acceleration function. So I'm going to do x double dash 3 is equal to 18 take 12 is 6. Let's just see if that looks right. 3, 6 looks right. And x double dash 1, this should be negative. 6 times 1 is 6. 6 take 12 is -6. 1, -6 looks right. Okay, what we want to know is its velocity when its acceleration is 0. Okay, so to do this one here, we want to know when x double dash t is equal to 0. That's when the acceleration is equal to 0. So we're basically asking the acceleration function, hey, when are you 0? 6t take 12 equals 0, 6t equals 12, t equals 2. And then we're going to ask the velocity function, so we're going to do we're going to ask x dash t, what is your value when t is equal to 2? Now, that's going to be 3 times 2 squared is 4, take away 12 times 2 plus 9. 12 take away 24 plus 9, that's 21, take 24, what's that going to be? Negative 12, negative 3. So its velocity is going to be negative 3 or 3 what is it, meters per second. Now let's just see whether that's right. So it's got a 0 acceleration. Going down here, velocity looks like it's negative 3 or 3 meters per second. Let's just see if I've done this correct as well. So it's acceleration. Let's go back and put a unit into all of these. So this is 6 meters per second per second. This is negative 6 meters per second per second. At what times and what positions will a particle have 0 velocity? Yep, that's fine for units. Okay, so we've got another question here. Okay, so let's work out the particle's initial position. Okay, so it's given by this function here. So its initial position will be the displacement function at time 0. So we're going to do x of 0 equals 9. Okay, and that is 9 meters to the right of the origin. Okay, it's position after 6 seconds. Okay, so we're going to say to the position formula, can you give us the position of the particle after 6 seconds? So that's going to be 36, take away 6 eighths are 48 plus 9. That's going to be 12, negative 12 plus 9 is negative 3. So it's going to be 3 meters to the left of the origin. Average velocity. Okay, you'll be tempted to find x dash t to do this, but don't. Right, so what's happening is that we've got this parabola, right? And 9 is the y-intercept, and it's probably, so what it's doing is going down, and it's going to come back up, okay? And what we want to get is the average velocity, which is the change in position relative to time over the first 6 seconds. So we don't need a derivative function here. All we're going to do is say velocity average is equal to x of 6 take away x of 0 over 6 take 0, which is 6. Now we've worked out both of these already. So this is going to be 9 take negative 3 all over 6, which is 12 over 6, which is not 6, it's 2. How far did it go in 6 seconds? Well, I'll be willing to bet it's not going to be the 9 meters back to the origin and 3 meters on the other side of the origin. Okay, so what's going to happen probably is that it goes down to the turning point and comes back up again. Okay, so let's find out where the turning point actually is by doing x of t equals t squared take 8t plus 4 squared take 16 plus 9. T take 4 all squared, what's that? Negative 16 plus 9, negative 7. Okay, so at 4, it's at negative 7, 9, so it goes down to there. Try that again. Goes down to the turning point, comes back up, and at 6 it was negative 3. Right, so here's what happens. It goes from 9 all the way down, or all the way to the origin, which is 9, all the way down to the turning point, which is another 7. Okay, so it's going to be 9 that it spends to the right of the origin, 7 that it spends to the left of the origin, and then from the left point on the origin, it comes back up here. So it goes from -7 all the way up to -3, which is a total of 4 units. So it's traveled 15 meters. Okay, its initial velocity. Okay, now we need x dash t. Okay, so x dash t is going to be 2t take 8. And not 0, we're going to do x dash 0, which is -8. Okay, and that means it's going at a velocity of 8 meters per second. Okay, and again, the negative sign indicates the direction of movement. Okay, that means that it's moving to the left. Okay, it is to the right of the origin, but the negative sign means it's moving left. Okay, where and when and where the particle is instantaneously at rest. Okay, so it's going to be at rest at this point here, which is going to be 4, but let's ask the derivative. So we'll just use some calculus anyway and see what happens. So we know that x dash t is equal to 2t take 8, 0 equals 2t take 8, 8 equals 2t. It's at rest at time 4, and x of 4 is going to be -7. We just know that because it's a turning point already. Okay, so when, so at time 4 seconds, and where at -7, time 4 seconds, 7 units or 7 meters to the left of origin. The velocity of the particle as it passes through the origin. Okay, so we're going to get 2 points here. We're going to get 1 and 2. All right, so our function is x of t equals t squared, take away 8t, what was it, plus 9. Okay, so this can't be factorized using integers, okay, or rational solutions. So what we're going to do is just slam this into the quadratic formula and say that t is equal to, okay, we're going to have negative b, which is 8 plus or minus the square root of b squared, 64, take 4 times 1 times 9, all over 2. That's going to be t equals what's that? That's 9 fours are 36. 64 take 36. 64 take 30 is 34. Take another 6 is 28. Root 28 over 2. Now we can do a pretty big simplify on that. That's root 4 times root 7. So that's going to be t equals 8 plus or minus 2 root 7 all over 2. Cancel, cancel, 4. So that's going to be t equals 4 plus or minus root 7. Okay, so this is when it passes through the origin. So that's this point here and will be at this point here. Has this got a restricted domain on it? Yeah, it hasn't. All right, so that's what time it passes through the origin. Okay, and what we want to do is get the velocity. So we're going to say x dash 4 plus root 7. We're going to stick that time in there to find out the velocity at that point. And so the velocity function is 2t take 8. So we're going to do 2 lots of 4 plus root 7 take 8 equals 8 plus 2 root 7 take 8 equals 2 root 7 meters per second. And let's do the other one. X dash 4 take root 7 is going to be 8 take 2 root 7 take 8, which is negative 2 root 7. So that's 2 root 7 meters per second also. All right, so there's really all you need to know about kinematics. So practice these problems down here, and as always, email me if you would like some assistance.